Hello viewers, welcome back to yet another retro channel. And today we have yet another in our Commodore 64 Repair-a-thon series. This is machine number 2, and I suppose without any further ado, let's get to it. As you can see, just like machine 1, this machine has been through its bath. In the process, as I said in the first video, which, by the way, I'll link the part 0 and part 1 in the upper right hand corner. For any of you who haven't seen those yet, please go ahead and watch those. But as I said in that video, I do tend to remove the power switches because I find that there is some risk to washing a machine with the power switch installed. The water that gets inside can displace some of the lubricant that's in there, and also it can take forever to dry. So I'd go ahead before I wash a board and I remove the power switch. So our first step here today is to replace this power switch so we can get going. So let me take care of that real quick. Okay, now that we have our power switch back, we can go ahead and retest our voltages as we did the last time. Since it's been through a bath, since things have happened to it, it's a good idea to retest the voltages that we may have already seen, but make sure that things didn't go bad on us. So first we will check our 5 volts being generated by the onboard voltage regulators, the 5 volts and 12 volts that go to the VIC-2 and the SID chip, and we check those on the right hand pin of the voltage regulator. This should be 5 volts. Oh, helps if we turn on the machine first. So this should show us 5 volts, 4.97, that's good. This one should show 12 volts, 12.21, that's fine. A little high, but it works. Next we check our 5 volts coming from the power supply, and we're going to check that on the CPU. That's pin 6 and pin 21 for ground. Okay, 4.59, that's low. That's going to probably indicate that we have a short somewhere on this board we're going to have to locate. But let's check the 5 volts at the user port. 4.54, again, that's very low, so that's probably indicating that we have a short somewhere on the board. And we'll check our AC voltage at the user port, 10.4, that is actually fine. So I think we're going to find that we have a short somewhere on this board. But where that leaves us immediately is looking at this board. This is not going to be as simple as the machine 1, because we only had 2 socketed chips on the entire board, and that was the VIC-2 and the SID. Now the SID I'm going to set aside and not bring back into this until the very end, because 1, that can cause black screen issues if it's got a problem, and 2, I don't want to risk if it's good, I don't want to risk damaging it while I'm doing the troubleshooting. So the SID will sit off to the side. The VIC-2, we're going to need that to do any testing, so we're going to have to check to see if that is a working chip. And to do that, I'm going to bring back the ZIF board one more time. Okay, you'll all recognize the ZIF board from the video where I built it and from the previous testing that I've been doing, Machine 1, and the work on the EEPROM PLA that was so tragically unsuccessful. We're going to hook up video and power, and we're going to pull our known good VIC-2 chip and drop in the VIC-2 chip from the board Machine 2 that we're testing. So there is the suspect VIC-2, and we'll take a look and see if we get any output. And we get a gray screen. So that is going to be a problem. We did see, in the initial testing, we did see a gray screen. So that tells me that we very likely have a bad VIC-2 chip here. Now, I will do further testing on that at some other point, but for now, we are going to call this one bad. Add that to our pile of dead chips from the Repair-a-thon, and I will reach and grab one of my limited number of replacements. There's a tested good R9 chip, or R8 chip. I'll just verify that this one is still good by putting it in the ZIF machine. And it is. So we can take it out, return the ZIF machine's VIC-2, and put the ZIF machine away. Get the test machine back and populate it with our replacement VIC-2. Now that's not a great thing to have happen. The VIC-2 is an expensive replacement part. These R8s, I've just been looking, and on eBay, the R8s are going for about $77, not including tax and shipping. So that's an expensive replacement. And of course, if you can get your hands on a VIC-2 Kawari, the FPGA replacement board, the minis are going for, I think, $95, and the large boards are going for well over $100. And that's if you can get them. Right now, they are currently out of stock. So replacing a VIC is not a cheap thing, and not something you want to see happen during a repair. But it is what it is. So get this VIC-2 back in its socket. Oh, I forgot the first rule of C64 repair. Deoxit that socket. Go ahead and hit the SID socket now too, since it's open. This can of deoxit is running dangerously low. Fortunately, I do have another can available. This cans leak so badly around their nozzles. All right. VIC-2 back in the socket. Nope, I missed. Oh, where's my chip lifter? There it is. What I did there, in case you can't see it, is I put the chip in one row of pins off. I don't think I'm going to be able to use this because of how I put that in there. So we'll have to do it the hard way. Come on. There we go. Make sure I didn't bend anything up. Nope. And let's see if we can get it in the right holes this time. Having a significant amount of difficulty getting pins on one side to enter the socket. There we go. All right. So now, knowing that there is probably a short on this board, I don't expect to get anything out of this, but I'm going to go ahead and hook this back up and see if we get anything. Just black screen, which is not unexpected. So now we need a dead test cartridge to see if that could tell us anything. Okay. Dead test. Let's see what dead test has to say. Well, we got one flash there for a moment, which implies we have a bad memory chip. And the memory on this board, of course, all 8 chips are empty RAM. So, not surprising that there's a memory error. And that could be where the short is coming from as well. What I'm going to do is I'm going to actually turn this on and leave it on for a bit and see if I can detect any of these RAM chips being particularly hot. So we're going to give that a few minutes. I don't want to go just indiscriminately desoldering chips and putting sockets in, because of course every time you do that you risk damaging the board, pulling, lifting traces, scratching things, doing damage that you then need to bodge around and fix. And so I would ideally like to identify which of these RAM chips is the issue. Now I'm not feeling anything at this point out of the ordinary. They are getting a little, they're warming up, but they're not getting hot. I'm going to check these other chips as well to see if I can find a source for that short circuit that we're getting. Take out the dead test cartridge here. Make sure everything's getting selected. With the dead test cartridge in, of course, the ROMs are never selected, so you might not see the same problem using dead test as you would with the dead test out. And of course, the VIC-2 is getting very warm, as it should. Not feeling anything particularly out of place for the logic chips. While I continue to let those warm up, let me step away and find my thermometer. Okay, so I'm going to start probing some signals now. What we need to do first are the basics. We've already checked voltages. We know that we got a low 5 volt on the chips, so we suspect a short. But let's take a look at some other things. For instance, let's take a look at the reset line on the CPU. Now, what you want to see from the reset line is you want to see it start out low. When you turn on the power, you want to see it low to start, and then after a half a second or so, it should go high so that the CPU is no longer in reset. So I'm going to probe pin 40, which is the reset line. As you can see, it's low right now. And when I switch on, after a split second, it goes high. So the reset line is good. The next thing we want to do is start looking at some address and data lines. And on the 6510, the address lines start at pin 7 and go to pin 23, skipping pin 21 because that's ground. Well, let's start at pin 6, which is the VCC. We'll take a look at that again. 1, 2, 3, 4, 5, 6. This should be 5 volts. What we're actually getting is, well, actually it's getting close to 5 volts now. So line 6, line 7 is address line 0, and we need to change our time base here. So address line 0 actually doesn't look bad. I apologize for the camera on the scope. It has a habit of over attempting to autofocus, so it may change in and out of focus there on you. I apologize for that. Here's address line 1. And again, that looks relatively normal. 2, still relatively normal. 3, good. 4, good. 5, pretty good. A little overactive maybe, but 6, good. What I'm looking for right now is that the signals are valid. That they go all the way down to 0 and they get up, well, in this case, you're looking at something like 3.5 to 4 volts, but that should be enough to trigger a 1. Again, good. Okay, address line 8 looks to be stuck high. So that's going to be a suspect. Address line 8, I should write that down. Address 9, also stuck high. 10, no, 10 looks good. 11 looks good. 12, yeah, A12 stuck high. A13 stuck high. A14, sorry for my hand blocking your view, stuck high. And 15 stuck high. So we have 5 address lines that are stuck high. Now we start getting into the data. It starts at pin 30. Data 7. That doesn't look right at all. That's not getting all the way to 0. So D7 looks off. D6 looks off. D5. Well, that's just 4, 3, yeah, 2, 1, and 0. All look off. Now while we're here, I'm going to go ahead and take a look at the clock signals. Clock 1 in, I'm going to need to turn on measurement. Okay. And measure our clock in on pin 1. That is showing 1.02 megahertz. That's perfect. And our clock out on pin 39. That is also 1.02 megahertz, so that's perfect as well. And check our other signals on the CPU while we're here. We're going to check ready on pin 2. That I don't think is right. Pin 3, IRQ, nothing there, so that's fine. Non-maskable interrupt. Okay. AEC, I believe, is not connected on pin 5. So I'm going to say right now, it's starting to look like the CPU might be an issue. It has a lot of bad signals, and what I'm going to need to do is find out if there's any other places on this board where those particular signals are common. So it's probably best for me to look at where the address lines 8, 9, 12, 13, 14, and 15 go. If there's one place that those go where, for instance, 10 and 11 don't go, that's going to be a suspect location. Now, I'm going to need to step away and look at some schematics and see if I can figure some of this out. And I will be back shortly, and I'll show you what I found. So, after some looking through the schematics and also after some additional testing, once I, of course, properly seated the VIC-2 chip and got the CAS and CAS-RAM working, I took a look back at the signals that we looked at before, and 49, 38, 37, starting on the data bus, as you can see, the data bus is not doing the same thing as it was before. The data bus actually looks better, but not perfect. We're still getting some mid-range stuff. But I think more importantly, I looked at the address bus again. Starting on address line 0, looks good. 1, looks good. 2, looks good. 3, looks good. 4, looks good. 5, looks good. 6, looks good. 7, looks good. Now, starting with address line 8. Oh, now that's looking good. 9. Okay. You can see on 9 there's some little half. There's some half signals. Those don't look good. Let's back at 8. 8 also has some of these little half signals that don't look good. 9, 10. Well, 10's looking better than it was when I checked it a little bit ago. 11. This is odd. This is not what I was seeing. That is address line 12, and it's constantly high. Address line 13, constantly high. Address line 14, constantly high. And address line 15, constantly high. So those don't look great, and some of the others did, looked a little suspect. That could be. Let me look again. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6, 7. Address line 8. Address line 8 is actually looking somewhat good. Address line 9, however, that's ugly. Yeah, those little pulses aren't right. So that's address line 9. Address line 10. Mostly okay. 11. 11 actually looks pretty good. 12, 12, 13, 14, 15 are always high. The only other place that I can find 12, 13, 14, 15 all on the same IC on the rest of the board is the PLA. And as we all know, the PLA is a common failure point anyway. So since I have now at least a hint of a reason as to why to suspect the PLA, I think it's time to desolder it and check it out in the ZIF board. So I'm going to go ahead and do that. We're going to heat up the desoldering iron. While that's happening, I will add some fresh solder to the PLA to help in the desoldering process. Okay, now that we have the PLA out, let's grab the ZIF board. Hook it up. Make sure it is still working. And it is. So let's go ahead and pop out the known good PLA and put in the PLA from the suspect machine. And see what happens. Well, no. Well, it's partially working. What's going on here? Let's try reseating that. Well, that time we're getting a black screen. Try reseating it again. Make sure our pins are intact. Okay, we definitely have a problem with this PLA. It's not reliable. It may be marginal, but we're going to call it bad. Add it to our pile of bad chips. Grab another Gal PLA. Use the ZIF board to make sure it's working. And it is, sort of. These using the pin headers on these with the ZIF socket is not always the most reliable thing. So yeah, that's working. So what we need to do now is go back to our test board and add a socket for the replacement PLA. Now, before we do that, we'll take a close look underneath the PLA to see if we see any damage. Make sure that the holes are clear, which they appear to be. We have any damage on the back? I am not seeing any. So let me grab a 40-pin socket. Or, sorry, 28-pin socket. I can't count today. We have our 28-pin socket. Make sure our notch is aligned at the top. Grab our blob of blue tack. Stretch it out. Use it to lock our socket in place while we tack a couple of corners. Go ahead and tack a couple of corners in. Remove the blue tack. Melt each of the corners while we make sure that the socket is flush to the board. Give it a little check. Yep, we're good. And go ahead and solder in the rest of the pins. Okay. Give that a little cleanup with some IPA. Look it over closely to make sure everything looks good. And all those joints look good. So let's take our gal PLA and insert it in the socket carefully. Reconnect power and video. And see what we get, if anything. Well, we're getting about the same thing we were getting before. So that did not do the trick, even though the PLA was bad. So the PLA was bad and something else is bad. Fine. All right, let's try the dead test now. Still black screen. Okay. Let's take another look at those signals, see if that did anything. Let's see. It was 12, 13, 14, and 15 that were the worst. So 12. Now I'm getting a clock signal on 12. 13, still just high. 14, odd. 14 is jumping around all over the place, so that's not good. And so is 15. Interesting. Oh, lost my ground lead. That's what happened. Try that again. So 12, 13, 14, and 15. That's 12. Oh no, so that's 11. That's 12. And I'm getting a 1.02 megahertz, what looks like a clock signal. 13 is just high. 14 is just high. And 15 is just high. So we changed one thing. We got a 12 megahertz or 1.02 megahertz signal on A12, and that may be because we have the dead test in there, which we didn't the last time. So let's try looking at it without the dead test. There is 12, just high. So we're getting the same things we got before. We didn't improve anything by swapping out the PLA. 12, 13, 14, and 15 only exist all in one place on the PLA. Or do they? They actually exist in one other place altogether. And that is, let me show you here. That is on U13 74LS257. On this board, U13 is a Moss branded part. Now I did suspect this earlier, so I tried clipping one of the pins and seeing if I had any different results. I didn't, but this is a Moss branded part and they are known for failure. This is the only other place that I know of on the board that has address lines 12, 13, 14, and 15 on it. So this is our next suspect. I'm going to go ahead and pull this chip. You couldn't see any of that. That's my fault. I forgot to take that schematic off the screen. Suffice it to say that I added solder to the legs of the chip that I'm about to desolder to help in thermal conductivity and to loosen up some of the potentially lead-free solder that they might have used soldering that to the board. Being that it's a Moss chip, I'm sure it's never been desoldered before. It's factory fresh. No one would replace a bad chip with a Moss unless they were desperate. There we go. I will check that. We'll go ahead and I've got the chip loaded into my TL866. We will load up a 74257, I believe it is. 74257. Test. And we're getting an error. So this chip is bad. All right. So I need a 16-pin socket and a fresh 257. Okay, I apologize for that. My recording computer crashed on me. I had to reboot. So I don't know what, if anything, you missed. I put the 74LS 257, or the MOS 7708. I put that in the XG, or in the TL866 programmer, which is capable of testing logic chips, certain logic chips, and it did fail. So I am going to go ahead and install a socket and put in a new 257. So here we go with that. Want to check real quick, make sure there's no damage on the board from desoldering. I don't see any. So we'll go ahead and fit the socket. Get our blue tack out again. A quick inspection. Everything looks good. So now we can power the board back up, connect to video, and see what we get. Wait, we have to put the actual chip in, don't we? Where's my, there it is. Lead former. The new 74LS 257. And here we go. Well, we're getting closer. We got a ready prompt. We didn't get the correct basic screen though, so we might have a problem with our basic ROM. We'll have to take a look at that. In the meantime, I'm going to pop in dead test and see what we get from that. And if that goes well, we'll go ahead and put in the diagnostic ROM. Oh, we've got a memory error. Okay. 1, 2, 3, 4, 5 flashes, 6 flashes, 7 flashes, 8 flashes. Eight flashes. Okay. And as you can see from the diagnostic, or the dead test manual up there, the 8 flashes means U21, and U21 is this little guy right here. Now, as I said at the beginning of this, these are all MT RAM chips, so I'm not surprised that we're seeing RAM failures. I may fix this one only to find that another one is bad. So let's go ahead and get the desoldering gun heated up. Heated back up. In the meantime, I'm going to add a little fresh solder to the chip in question, which is this guy right here. Slides right out. Nice. Now, okay, we're going to give this chip a little read in our tester. Did not test good, so that makes sense. Let's get another socket, and I'll actually get several sockets and several 4164s. And that one tests good. So I've got 4 sockets and 4 RAM ICs. 3 of those I need to retest. That is the bad MT RAM that's going in the pile of bad chips from this repair-a-thon. That 41, I'll have to get those out later. Set those aside. Now to put a socket in place of the chip we've already removed. Okay. Check our work. Missed a pin. Don't want to do that. There we go. Check our work. Don't see any bridges. Nice joints, nice and clean. And one of our tested 4164s. There we go. See what we get from the dead test. I'm expecting more flashes. How about you? Three, 4, 5, 6, 7. Okay. 7 flashes this time. And 7 flashes. We look at the dead test manual again. That's going to be U9, which is going to be him right there. So, here we go again. Let's desolder U9. Easy out. Let's not bother with the tester this time. We'll just go ahead, check the board for damage. I don't see any on the top or on the bottom. So, socket number 2. All right, ridges, and looks like good joints. So another of our tested good 4164s. There we go. Power. And video. And dead test. 3, 4, 5, 6, 7. What? 1, 2, 3, 4, 5, 6, 7, 8. What? 4, 5, 6, 7, 8. We've already done 8. 8 is U21. That's interesting. Okay. I'm going to check some continuity and make sure we're getting through everywhere we're supposed to get through. The RAM on the 64, most of the pins are common except for the data pins, and the data pins are 2 and 14. 2 and 14 are actually tied together, so I should get continuity here, and I do. 2 and 14. I should get that on every chip. And then the rest of the pins should be common across all the RAM. Okay, pin 1 is not showing common. What is pin 1? Make sure. This is a 4164. Pin 1 is VBB. I don't believe that's actually connected, so we're probably good there. Okay, now okay, let's look for pins I might have shorted together. That was me touching the probes together. Okay, I didn't short anything. Why are we getting 5, 6, 7? Well, 6 this time. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That means that more of the logic is messed up. So we're going to have to dig into that. We'll be back. Hello, me from the future here. I hate to do this to you, but unfortunately this video is getting a little long, or actually a lot long, and I think it's time we call it a day. And we'll pick this up again next week in Commodore 64 Repair-a-thon Part 2B. In the meantime, if you've enjoyed this video, and I hope you have, I know it's getting a little long, please go ahead and give it a like. If not, you know what to do there too. Of course, if you do dislike the video, I would appreciate it if you'd add a comment as well telling me what it is that you don't like about it. That way I can work on improving my videos for the future. I want these to be as enjoyable for you as possible. If you haven't already, please go ahead and subscribe to my channel. Every subscriber helps, every view helps. And ring the notification bell. That way you will be notified when the next video is available. For instance, you'll be notified as soon as Part 2B drops on the channel. And apart from that, that's going to be it for today. So take care, be well, be safe, and we'll see you next time. Thanks for watching. Bye.